So at the end of the last video, I said in this one we get into resonance, but I want to delay that just a little bit because I want to say a little bit more about this beating phenomenon. And in particular, try to understand what the sort of envelope curves, the sort of longer wavelength sine curves that are enveloping the oscillation, what those sine curves are, or those sinusoids are. And we're going to do this through the use of some trig identities, okay? Now, to get started here, maybe the best way of doing this is to do a really concrete example, right? We've been pushing symbols around quite a lot. Let's push some numbers around. That sometimes makes students more comfortable, okay? So let's do the following example. Maybe I'll do it in blue. So let's look at the harmonic oscillator 0.5 x double prime plus 8x equals 10 cosine pi t. So this is a periodically forced undamped harmonic oscillator, okay? And in fact, this is the example that I drew from the textbook. So the picture of the solution is exactly this one right here. It's exactly this. Okay. Let's see how we get from the from this equation to that solution. We're going to toss in, by the way, some initial conditions as well. We're going to declare that x of 0 is equal to 0 and that x prime of 0 is also 0. This will help simplify our life quite a bit. Okay. Now, if we look at the general solution that we've got up here, we can, if we can figure out all of the different elements that we've got, then we can sort of match what we've got in our equation with what we've got in the general solution. Okay, so for example, we can identify m here pretty easily. M is 0.5, right? We can also identify k. K is 8, okay? Those two quantities together are going to allow us to figure out what omega naught is, because recall that omega naught, which is the square root of k over m, is the square root of k over m. And of course, that's going to be the square root of 8 divided by 0.5. How many halves go into 8? Well, that's 16. And the square root of 16 is 4. So in this case, omega naught is 4. Okay, cool. And I think that takes care of many of these things. Oh, we also need to know, I'm looking at the general solution here, we also need to know omega and f naught. Okay, but these are really identifiable from the forcing function. In this case, the forcing function is 10 cosine pi t, and that's supposed to be f naught omega t in our setup. So we can identify that omega is pi, okay, and that f naught is 10. So we've got all the elements here that we need to write down x of t. From all of this, we can conclude that x of t, so really, just to be absolutely clear, what I'm using here is all this information up here. Okay, that's what I'm using here. X of t is equal to f naught, which is 10, divided by m, which is 0.5, times omega naught squared, that's 16, minus omega squared, which is pi squared. Okay, that's the coefficient there, times cosine of omega t. I don't even have to think. I'm just looking up my symbols here. Okay, plus c1 cosine of omega naught, which is 4t, plus c2 sine of omega naught, which is again 4t. Okay? So you see, hopefully, the value of doing things in general is that it allows you to then apply the general solution in full generality with all the symbols to your particular situation. Okay, so that's the general solution to the harmonic oscillator, to the differential equation, but we have initial conditions that we can use to figure out what x of what the constant C1 and C2 are. So the first initial condition is that x of 0 is 0. So let me look at that one first. So x of 0 being 0 means that 0 is equal to x of 0. And that means when I plug in 0, what I get is 0. But on the other hand, if I plug in 0 on the right-hand side, I get, oh, and I should simplify this. 10 divided by 0.5, how many 0.5s go into 10? Well, there's 20 of them. So this is really 20 over 16 minus pi squared. In fact, I don't even need parentheses now. Okay? Times cosine pi t. Oh, but the whole point is that when t is equal to 0, cosine pi t is cosine of 0, which is 1. Okay, so I get 20 over 16 minus pi squared. And then I have c1 cosine 4 times 0. That's cosine of 0. That's just c1. Okay, and then the sine term here, this one here, dies when t is equal to 0. Okay, this one was c1, this one dies. So we get this equation that 0 is equal to 20 over 16 minus pi squared plus c1, and therefore we can conclude that c1 is equal to negative 20 over 16 minus pi squared. Hopefully that's clear. And so we know c1 now, which is great. Great news. Okay? Now, what about the second initial condition here, that x prime is 0? So, well, we should figure out what x prime is, I guess. X prime of t, and you get used to this, start to have this feeling that whenever you see a sign, it's kind of like when you plug in 0, that's always going to die, right? So the thing that, I'm not even going to really think. What I'm going to do is notice that if I take the derivative of this, I could really stress out about what the derivative of that thing is, but what I know is that this is going to be some constant a, and I'm not even going to think about what a is. It's going to be some constant a times sine of pi t. Okay, I don't know what the constant a is. I don't care is the point that I'm trying to make. And similarly, if I take the derivative of this thing here, that's also going to be some constant, some other constant times sine of 4t. Because I know what I'm going to be doing is plugging in 0 into all of this. Do you see what I'm saying? The derivative of this one I might actually care about because that's going to generate for me a cosine. So I'll be careful on this one. It's 4c2 cosine 4t. I don't care about what a and b are. Why? Because now I'm going to plug in 0. And I get the 0 is equal to x prime of 0. The sine terms die. That's the point. And what I'm left with is 4c2. Which of course implies that c2 is equal to 0. Okay? So in this particular situation where your t is 0, you can kind of compute in this way. And I'm hoping that you're sort of leveled up enough in your math skill that you can reason through stuff like this. So in particular, the solution that we are after is x of t is equal to where is c1 and c2? So here I'm looking right here now at the purple, and I'm going to use these values for c1 and c2. Okay, and what I get is 10. Well, okay, I get 20 over 16 minus pi squared times cosine pi t. And then I have c1 being equal to negative 20 over 16 minus pi squared times cosine 4t. And then c2 is 0. So this is my solution to my differential equation. Now, again, I pulled this from the textbook. So what I'm saying is that if you plot this boxed blue thing, this solution here, if you plot it, then you're going to get this as your graph. Okay? This is the graph of this, is all I'm saying. Okay? Of course, we're plotting the t in the horizontal direction and x in the vertical direction. Alrighty? Now, how can we see this a little bit more with a little bit more clarity? Well, what I'm going to use is a trig identity. I won't prove this trig identity. I'm just going to shove it down your throat and you're going to accept it. Here's the trig identity. The trig identity is going to be it's a way of converting a difference of cosines of different frequencies, or a difference of cosines period, into a product of sines. Difference to product. It allows you to write two. Well, let me write it like this: cosine of b minus cosine of a is equal to 2 times sine of a minus b divided by 2 times sine of a plus b divided by 2. This is a trig identity. And again, I'm not going to justify it. It looks arcane because, it kind of is. You don't really learn this one in the normal course of events, but it is true. And, challenge, can you derive it yourself? How can we apply this trig identity? Well, we can try what we have. If you look at x of t in blue, what we have is a difference of cosines. I can make this more apparent by factoring out this 20 over 16 minus pi squared, right? So x of t is equal to 20 over 16 minus pi squared times cosine of pi t minus cosine of 4t. Close brackets. Now we compare what's inside the brackets with the left-hand side of our trig identity. We ask ourselves, what's playing the role of b, what's playing the role of a? This is playing the role of b. Maybe I'll do this temporarily. This is playing the role of b here, and this is what's playing the role of a. Okay? So that we have cosine of b minus cosine of a. You feel it? So then, what does this become under this trig identity? Well, it becomes 20 over 16 minus pi squared. Alrighty, times, okay, so I just got to say I would do this. So I have 2 sine of a minus b, so that's 4t minus pi t, which I'm going to write as 4 minus pi times t, and then divided by 2 times sine of a plus b, so that's going to be 4 plus pi times t divided by 2. Good. Okay? And now what I can do is pull out the 2. All right? If I pull out the 2, I get 40 over 16 minus pi squared times sine of 4 minus pi times t divided by 2 times sine of 4 plus pi over 2 times t. Okay. Now, first question. What are the envelope? So if this blue thing here is pictured by this thing here, what, and I've told you that the envelope curves here are themselves sinusoids. Like this. Okay? You can see that manifesting in this expression. Because what we have here is a product of sine waves, a product of sines. One of these is the sort of shorter wavelength sine. Which one is that? That's the one with the greater angular frequency, right? And 4 plus pi over 2 is certainly going to be bigger than 4 minus pi over 2. Just think about what pi is. It's 3.14. 4 minus pi is like less than 1, and then divided by 2, it's even more less than 1. 4 plus pi is like 7 or something like that, right? 7.1415926. Divided by 2 is 3.6, whatever it is, yeah? 3.515, whatever it is, yeah? So in particular, this is going to be our envelope curve. This is the thing that's going to envelop the other sine wave here. Okay? You might try plotting this in Desmos. I just don't have the patience to do that right now. But if you don't believe me, you should try it. This is the envelope curve that is determining the sort of shape of this oscillation here. Okay, like this, and then like this. But here's what here's what I want to say. Okay, what's the maximum displacement of our harmonic oscillator? Well, this is a sine wave which oscillates on its own between 1 and -1. Similarly, this oscillates between 1 and -1. So the product of these oscillate between 1 and -1. They can't get outside of 1 and -1. So the maximum displacement, or the maximum amplitude that we're going to see here, is controlled by, is 40 over 16 minus pi squared. Now I'm going to quickly look up on Google what that number is equal to. 40 divided by 16 minus pi squared. That's about 6.5248. Let's look back at our graph here. Does 6.5248 seem plausible? 6.5 seem plausible? I kind of think so. This is 10 and this is 5. You can read that from the graph, right? And it seems to me that the maximum displacement is happening like there-ish, yeah? And that seems to me to be around 6.5. Fair enough, right? Pretty close, okay? So in other words, you can read off what the maximum displacement is from this. Why on earth would you care about the maximum displacement? Well, because if you have something like, a water tower or something like that, or some kind of structure which is vibrating, you want to know how far off from the equilibrium it could get if exposed to some kind of external forcing. Because that maximum displacement might tell you whether or not your structure will collapse. Okay, so things like maximum displacement matter. So let me just conclude and then we'll end the video, and then I'll talk about resonance in the next one, I promise. The maximum displacement in this case would be given by 40 over 16 minus pi squared. That's the maximum displacement from equilibrium, I should point out, for our periodically forced harmonic oscillator. Okay? All right. That's enough for this one. So long.